Today I'm going to be talking about Unicode and you. It's going to be a guided tour through, quote, the world standard for text and emoji. I didn't make that quote up. You go to the Unicode website. That's the title of their homepage. Whatever. That's what they want to call it. That's okay. So basically, if you are unfamiliar with Unicode, we'll get into what it is. But in this talk, we're going to talk about how we're going to discuss how plain text, like text in a text file or an HTML document or your code, how that gets turned into bits and bytes that the computer can understand. First off, some of you might not know who I am. My name is Sean Newman. Most people just call me Newman. I'm a lazy fifth year at this point. I'm a master's student, finishing up my master's degree this semester and next semester. I used to do a little bit of competition stuff here and there, but not too much. I don't really do that much anymore. And I'm pretty interested in cryptography, and I'm not talking about like cryptocurrencies like Bitcoin. I'm talking about things like AES. I think it's pretty cool. I've done a presentation on some crypto attacks in the past, and I might be doing some in the future. Stay tuned. So before we jump in, let's go over a quick agenda of the topics we'll be covering today. First, we'll talk about the text encoding world before Unicode was a thing. Mainly, we're going to touch on ASCII and code pages and what those are and some of the problems with them that led into Unicode. And then we'll talk about what Unicode is and go over some of the basics of Unicode. Next up, we'll talk about the various encoding forms that are commonly used. That's UTF-8, UTF-16, and UTF-32, if you've heard of those before. After that, we'll touch on some kind of weird stuff that if you're a Westerner, like, if you're American, you mostly ever just used English before, these things might seem a little strange to you. Because we're used to having, just like ASCII, you don't have to use that many characters, but we'll get into that. There's some interesting stuff that Unicode does to deal with all languages of the world. And then we'll finish up by talking a little bit about emojis, which are much weirder when it comes to Unicode. And if at any point, you have any questions, I've got the Discord questions channel open. I've got Twitch stream chat open. I don't have Zoom chat open, sorry. But feel free to ask me a question. Let me know. Guys in the stream, John, Enzo, interrupt me. But otherwise, let's get into it. So first up, ASCII. Sure, fair few of you are familiar with this, specifically this ASCII table, especially. It was one of the first basic text encoding schemes, or rather one of the really common ones that's still fairly prevalent today. It only used, 7 bits to encode text. And when I'm saying encoding, I mean representing as bits, ones and zeros. So if you encode an A, you're representing it as ones and zeros in binary somehow. So it used 7 bits, which gave you 127 different possible values. So you can encode 128 characters. And that means 7 bits, well, a byte is 8 bits. So what they decided was, okay, the first bit is always going to be 0. So when you have ASCII, the first bit is always 0, and then the next 7 bits contain whatever your character is. And that was enough for A to Z, upper and lowercase. We got some numbers here, we got some symbols, a bunch of control characters, most of which used to be really useful, but we don't use a lot of them these days, some of them. And that, for some folks, that seemed like enough, right? That's all we need. No, actually, there's more than just English in the world. I hate to break it to you. If you didn't know that, I'm sorry. Also, some letters, even in English, it's more common in other languages like French and Spanish, but even in English, we have words like resume that don't just use those normal 26 A to Z characters that you see here. Like in resume, you have the E with the little accent on it, and that's not represented in ASCII, so how do you type that out? Also, sometimes you want more special characters. Like back in the day, menus used to be represented by special characters. Like you can see here, we've got some lines that you can use to construct like a menu or a simple terminal UI, like this table that's right here. So code pages seemed like a decent way of handling this. Just code pages to the rescue, sort of. Not really, but we'll get to that. Since with ASCII you're only using 7 bits, and the first bit in the byte, the highest order bit, is a 0 all the time, you could just flip that bit to a 1. You use the other half of the byte, and now you have 128 other characters that you can encode. And that's what a code page did. It would use the remaining 128 values in a byte that ASCII did not lay claim to encode a series of other characters. Sometimes, like this one, you'd have more special characters for menus. Other code pages, like Latin 1, might have more variations of like vowels and maybe some consonants that have accents for languages that use a lot of accents on Latin characters. Other code pages could encode other alphabets, like Cyrillic or the Greek alphabet. But code pages aren't perfect. For one, not all languages can fit all of their characters into 1 byte, especially a lot of Asian languages. For example, Chinese. They have thousands of characters. There's no way you're fitting that in 1 byte. Another problem is, even if you're just loading like an English language web page, you feel like it's pretty standard what characters are going to be on that page, right? Well, if you don't know what code page was used to encode that document, it's going to render all scrambled. Characters aren't going to show up right. Maybe instead of a new line, you have, I don't know, whatever this is, a circle in a black rectangle. It's going to look totally wrong. And there was hundreds of code pages, so you'd have to try each one, and you wouldn't know what they used. It was a mess. Code pages were a total mess. So one day, a bunch of people got together and decided, all right, screw this code pages mess. We're going to create a single standard that describes all the characters that we ever need. And they made Unicode, which is an attempt to describe pretty much every writing system in the entire world. That's at least their goal. It's a pretty ambitious goal, and as a result, Unicode can get pretty complicated. Unicode itself is this massive database of characters called code points, and we'll get into what a code point is in a second. But for now, you can just think a character is a code point is a character. Originally, or at least early on in the Unicode standard, they had planned for everything to fit into just 2 bytes, because that seemed like enough. That's about 65,000 characters, right? That should be enough for all the characters in the world. Turns out that's not the case. And it has been expanded since then. Right now, the highest Unicode code point can be encoded with 21 bits. 21 bits for the highest code point, which is a little bit less than 3 bytes. That 21 bits give us a capacity of about 1.1 million characters, or at least that's how many they have reserved at the moment. But if we need more, they maybe expand the Unicode code point size in the future. So, what are code points? I said that word a few times. What the heck is this code point thing? Well, in the world of Unicode... Huh? Something happened? We good? Okay. In the world of Unicode, a code point is an integer that gets assigned to a single character. And it's less... This is where it gets kind of interesting, because it's not really... Code points aren't really characters, and they're more like the idea or the concept that's represented by a character, if that makes sense. For one, code points are independent of how a character might be represented in a font. So, for example, we have here Latin capital letter A. You might have this bolded. You might have a really fancy script font. Maybe you have a serif font, or a sans serif font. Those are all represented by the same exact code point. Also, different characters that may look the same or look very close to each other could have slightly different meanings. Like if you look into Unicode, there's a bunch of different characters that look like a Latin capital letter A, but they have different code points because Unicode decided that each one had a slightly different like semantic meaning. So code points can be kind of fuzzy, what is and what isn't a code point. And also it can be kind of a political issue even as to what makes two characters different and what might make two characters the same. For example, some characters that might be used by multiple different languages can have vastly different meanings based on what context. Well, like I said, code points can be different even if they appear the same, if they have different like semantic meanings. One case in this is Chinese characters, sometimes called Han characters, that are also used in some cases in Japanese and Korean. Now, these characters can have vastly different meanings between Chinese, Japanese, and Korean, but there's a ton of them. So back when Unicode decided we only want to have 2 bytes maximum, they couldn't fit all of 3 copies of each one of those characters in Unicode. So they did something called Han unification, which I'm not going to get into anymore here, but it was seriously controversial and a little bit complex. You need to get into kind of the history of the culture. So I'm not going to talk about that here, but if you want to know more about it, look up Han unification for more information. Anyway, back to code points. A single code point is written as capital letter U, a plus sign, between 4 and 6 hexadecimal digits, depending on how many you need, and then a unique descriptor in all caps. So for example, letter A is written as this, with the description Latin capital letter A. The AE character, this is the code point, and this is the description, and then the pile of poo emoji that we all love, it's named pile of poo, and this is the code point. And one thing to note, this hex representation is the hex representation of the integer that's assigned to that character. So A, it has the integer 42 in hex. I don't know off the top of my head what that is in decimal, but the hex value 42 in Unicode represents Latin capital letter A. So 1F4A9 in hex represents the pile of poo. So those are code points, and we've got tons of them. So code points get organized into these things called planes. And a single plane is a range of 2 to the power of 16 code points, which is about 65,536 code points, actually exactly. The first plane is called the basic multilingual plane, and it contains most of the languages that are commonly used today in the world. It's pretty much full at this point. Most of the space is taken up by those Han characters, that I was talking about. But most characters that you use every day fit into the basic multilingual plane. The last two, planes 15 and 16, are marked for private use. What this means is the Unicode Consortium, the people who manage Unicode, they guarantee that these planes are going to remain reserved for private use, and they are not going to assign any code points to these planes. You can use them however you want to encode whatever data. I don't have any examples for you, but they're there. In total, you have 17 planes that cover the Unicode code points 0000 to 10 FFFF. Just like it says, roughly 1.1 million code points. Currently, we have about 110,000 code points that have been assigned, with more that have been roughly mapped out for some ancient languages. Also, fun fact, the 16 planes after the basic multilingual plane, so planes 1 through 16, those are sometimes called the astral planes. So, bet you didn't know that. So let's start talking about so we're talking about all these code point things and these integers actually get turned into bits. How do they get sent over the wire, saved to file? Well, one example is UTF-32. I mentioned earlier that all code points can be represented by 21 bits. And so all 17 planes, the basic multilingual plane and the astral planes, can all be fit into a maximum of 21 bits. So what UTF-32 does is it uses 4 bytes for each character. Well, 21 bits is a little bit less than 3 bytes, right? So why don't you just use that? Well, 4 bytes is easier to do proper byte alignment with, and computers like operating with powers of 2, or at least computer programmers do. So we have UTF-32, it uses 4 bytes. And this 4 bytes is called the code unit for UTF-32. We'll talk about that a little bit more, but just know the code unit is 4 bytes. And with UTF-32, all of Unicode, fits into one code unit. You don't have to do any weird shenanigans. You just take whatever the code point integer value is and pop it into a 4-byte block. Like you can see here, the pile of poo, we've got this 1F4A9, and then you just put it into the 4 bytes like that, aligned to the least significant bits. As you can see here, we've got this one byte. The highest significant byte is basically unused here. So UTF-32, it is kind of wasteful in many cases. You don't really ever need that 4th byte, but that's just how UTF-32 is. It uses 4 bytes for each code point. For the letter A, the waste is even worse, you could say. It only uses the single least significant byte out of all 4 bytes. So this can be good because with the consistent size of code units, you can easily index to a specific character in a string. If you know that you're trying to grab the 4th character, you just grab the address at the beginning of the string, take whatever the index of the character is, multiply it by 4, boom, that's the address of your character. Easy peasy. That actually turns out to be less useful in practice than you would think, for a reason that we'll talk on later called Grapheme clusters. But anyway, one of the cons of UTF-32, like I said, is that it's dummy thick. It's a big boy. It uses a lot of data to store each things, to store each character. And if you're used to ASCII, where each character is only in 1 byte, well, now your file is going to be 4 times as big with UTF-32. So instead of UTF-32, you could use UTF-16, right? Because this A value it only needs 1 byte, and then some other values in the basic multilingual plane, they're only going to use those 2 bytes. So why don't we just lop off the 2 high order bytes and just use the 2 low order bytes? Well, that's what UTF-16 does. It's got a code unit of 16 bits or 2 bytes. Most characters, like I said, they aren't super big. All the basic multilingual plane, for example, can fit into 2 bytes. So for everything 0000 to FFFF, it can just fit in 1 code unit, like this A here. Anything above FFFF, so anything outside that first plane, needs 2 code units. And to do that, there's this thing called surrogate pairs, which we're going to get into in the next slide. But you might have remembered I said that early on, Unicode was only planning on using 2 bytes for each character. Well, when they said that, a bunch of early adopters to Unicode just hopped on and said, oh, UTF-16, this is all I need. Great. And so they started using UTF-16. And then Unicode expanded it to larger than 2 bytes, and then they had to introduce surrogate pairs. So, for example, on Windows, that's why you see wide chars everywhere. It's a decent implementation of UTF-16. We won't get into it, but there's some ways that it's not compliant with the UTF-16 standard. Just gonna take a little drink. If anybody has any questions, post them in the chat. Otherwise, I hate WCHARs. I do too. Fan 5152. I hate WCHARs as well. So, I mentioned a minute ago, surrogate pairs is how UTF-16 stores values that are outside the basic multilingual plane. And surrogate pairs are this fancy method for storing code points that require more than those 16 bits to encode. Basically what it does is it uses 2 special container code points that are reserved. There's this whole range of code points that Unicode reserves for this use. And each container has this, has this standard 6-bit prefix. And it has room on the other side for 10 more bits of data. So pair, you have 2 of these containers. So you have 2 containers, each with 6-bit prefix, 12 bits of prefix in total, each with 10 bits of data, 20 bits of data in total. So in total, you can encode with a surrogate pair 20 bits of data, which I said earlier, Unicode requires 21 bits. So how does that work? Well, with a surrogate pair, we know that we're only going to use a surrogate pair if the code point is above FFFF. So if we have a surrogate pair, or if we have a code point that needs to be encoded by a surrogate pair, we can just subtract hex 10,000. I'm going to say, I don't know how you say big numbers in hex, but I'm just going to call that hex 10,000. You subtract hex 10,000 from it, which essentially makes that 21-bit value a 20-bit value. Boom, now it fits into your surrogate pair. So when you're encoding, the first step would just be to subtract from the code unit, hex 10,000. You could put it into the surrogate pair. And then when you're decoding, you take the data out of the surrogate pair, re-add the hex 10,000, and then you get your code point. So with surrogate pairs, you have we have 2 surrogates. You have the high surrogate and the low surrogate. The high surrogate is the 2 high order bytes. The 2 bytes, each one of these numbers here is a bit. So we have 16 bits for the high surrogate, that's 2 bytes. 16 bits for the low surrogate, that's again 2 bytes. These are the high order bytes, these are the low order bytes. So for the high surrogate, the prefix is always going to be this binary representation here, 110110. The rest of it can be whatever it needs to be for the data to encode the code points. For the low surrogate, it's going to be a very similar prefix, 1101111. And then you've got all the data down here. It's your high surrogate and your low surrogate. So here's an example of doing a surrogate pair. We've got our pile of poo emoji. This is the Unicode code point. We're going to subtract hex 10,000 from it to get the value that we're storing in the surrogate pair, F4A9. We're just going to convert that to binary here, and then this hot pink purple. Sorry if you're colorblind. This hot pink purple is going to go into the high surrogate pair, or the high surrogate value, excuse me, and this teal is going to go into the low surrogate value. So we've got our high surrogate, and our low surrogate with the prefixes and the data containers. And we're just going to split them up. This is going to go down in here, and this is going to go down in here. Boom. Now we have stored a pile of poop with UTF-16. Yay! Moving on, we've got UTF-8, which is a much more common one. With UTF-8, it's got a code unit of 8 bits, which is 1 byte. For the first 128 characters, it's going to be identical to ASCII, which is great because if you have ASCII and you want to encode it with UTF-8, you've got that backwards compatibility. Above ASCII ranges, we start to need multi-byte encodings, which we're going to get to in a second. But a multi-byte sequence allows you to store every Unicode code point in between 1 to 4 bytes. So we have our A here. It's got the hex value of 42. That's just going to store the same thing as ASCII, 42, 1 byte. But with pile of poo, it's a little more complicated. With multi-byte sequences, you look at the prefix, the binary prefix, to determine how many bytes are being used for the encoding. So if you only have 1 byte used, then the first bit will be a 0, and that can store up to 7 bits of data. For 2 bytes, you've got this prefix that can store it to 11 bits. If you have 3 bytes, it's this prefix, so it's 16 bits, 4 bytes, yada yada. And then that's just for the first byte. So we have that prefix and then our data that's stored in the byte. For every other byte after that, there's this special prefix 10 that says, hey, I'm a continuation of a previous multi-byte sequence. I'm not my own character. Use me as a continuation. So if we want to encode a pile of poop, we take the poop. We've got our Unicode code point. We're just going to convert this into binary, and we see it's got 16 bits. So if we go back here, we see that for 16 bits, we want to use 3 bytes. So we're going to set up our prefixes and our data here into 3 separate bytes. I just split up the data into the little sections so you can see where they're going in. And then you put your 16 bits into the data sections of your multi-byte sequence here. In this case, we're going to fill up all of the data bits in those 3 bytes. But if you had a little bit less than that, like say if you had 12 bits, you would just use the low order bits. So you'd start from here and work your way up. And then any unused bits, you would just fill in with zeros. So that's how generally Unicode characters are stored as text, or stored as binary in plain text files. But what I just talked about were encoding forms. We got a knife hacker. Is there any advantages of multi-byte sequences over normal variants? I'm assuming this question means, is there any advantage to using this multi-byte sequence in UTF-8 over using something like UTF-16 or UTF-32 that's more consistent? The answer to this is that with UTF-8, it's much more efficient in the amount of data that you're using. If you only need 1 byte, like for example, if you're using ASCII characters, you're only going to use 1 byte. You're not going to have a whole extra byte of waste. If you need those 2 bytes, you get 2 bytes. If you need 3, you use 3. If you need 4, you use 4. In practice, UTF-8 generally ends up being, the file sizes for UTF-8 end up being a little bit smaller than UTF-16, but not by much. In general, I would say it's also, from an education perspective, it's good to use UTF-8 just because it introduces you to the idea early on that a single character might be represented by more than 1 byte. Knife hacker clarifies, no, var ints. Is there any advantages of multi-byte sequences over normal var ints? Not sure what you mean by that. Are you talking about like int 32, int 16, int 8? Sorry, you're gonna have to clarify that. I'll get back to that question in a bit once we get a little bit of clarification. So what I talked about, UTF-8, 16, 32, these are encoding forms. These are describe how a code point gets represented as bits in a file. And the encoding scheme is another thing that we have to worry about, which talks about how bytes are transmitted over the wire. If you remember networking, this is endianness. And yes, we do have to worry about endianness with Unicode sometimes. For UTF-8, this is taken care of for us. UTF-8 is actually the only encoding form, which is also an encoding scheme, because each code unit is 1 byte. So we don't have to worry about the ordering of bytes. But with UTF-16 and 32, we have a high order byte and a low order byte, and we have to figure out how to order those around. Or for, in the case of UTF-32, we've got 4 bytes. You need to figure out how to organize them. For UTF-16, this is typically noted by appending an LE or a BE to denote little endian or big endian. I assume it's very similar for UTF-32, but that's the difference between the encoding scheme, which is endianness, and the form, which just describes how the code point becomes bits. I also want to touch on scalars. A Unicode scalar is just a fancy, kind of another term for a single code point. But more specifically, when you're talking about encoding forms. So when you're encoding a single code point, that code point might have might take a different number of bytes to be represented. So we got this table here. You can see, based on what scheme or form that you're using, the code point could use between 1 and 4 bytes, 2 or 4 bytes, or even just 4 bytes entirely. And the scalar size is the size that that one code point takes on disk to be represented. So for something like a Latin capital letter A, its scalar size is going to be 1. For the pile of poo that we talked about, this takes 3 bytes, so its scalar size is going to be 3 bytes. Another interesting thing with Unicode is that not all characters are just, or not all code points rather, are just standalone characters. There's a lot of code points out there called combining marks. And if you've ever seen Zalgo text like this, you probably know what I'm about to talk about. Combining marks will modify another code point that typically that they come after. So if you're going to be using combining marks, typically you'll have a base character like this lowercase a here, and that's what's going to be modified by the combining mark. Then immediately after it, it's going to be followed up by another scalar representing whatever the combining mark is. So here we have an accent grave. So if you saw the Latin lowercase a and then the accent grave combining mark on disk, you would know to render the lowercase a with the accent grave. And you can combine these in all sorts of ways, like you can see here with the Zalgo text, to create lots of different meanings. In a lot of languages, these combining marks are used to specify specific meaning, pronunciation of letters. So they can be quite important to some languages where including or not including a combining mark can wildly change the meaning of a word or phrase. In some languages, the characters are formed entirely of combining marks. Some languages create their characters from multiple, like you take multiple smaller like base units and swoosh them together into one single character or one glyph that gets displayed, and that represents a single syllable. Unicode also provides what's called pre-composed characters, which is a single code point, because we couldn't make things complicated enough. it's a single code point that represents the base character modified by a combining mark or multiple combining marks. And if you want, you can use a pre-composed character instead of using the base followed by combining marks. When we talk about scalars and combining marks, we also get into grapheme clusters, which is a group, I'm going to read from the slide here, a group of code units that represent a glyph. So glyph here means however the character is visually represented. And that means, like, for example, here with the A with the accent, that would be a glyph. That's a visual representation of this code point, this character. Grapheme clusters can comprise of at least one or even more base characters, and as multiple combining marks. Also, grapheme clusters have these semantics to describe, based on the way the code points are ordered in the byte sequence, which base characters are modified by which combining marks and how those modifications are applied. So grapheme clusters can get pretty complex, and I only kind of barely understand them myself. But there's something interesting, if you think this is cool, something interesting to look into. Emojis in particular, a lot of them will abuse grapheme clusters to create fancier, different emojis that Unicode doesn't explicitly define. If you pull up the emoji keyboard on your phone, actually a lot of those aren't actually Unicode code points. They don't exist to Unicode, at least specifically. The vendors, the people who make those keyboards, and your, Samsung, Google, Apple, they combine different code points to create an emoji. So if a cluster is just a sequence of code points or scalars, then how do you know when a cluster ends? Well, how do you know when a cluster ends and a new one starts? It depends. There's a lot of really complicated rules that often depend on context and are usually really specific to the language that you're working in. So just like Weissman said, it depends. Want to finish up by talking about a few specific emojis. The pile of poo that we've been working with. This is a single code point emoji. The Unicode Consortium saw fit to declare pile of poo as a standard. So there you go. Bunch of folks in a committee sat down, decided we want a pile of poo in Unicode. It's pretty interesting if you ask me. But a lot of other emojis, like I said, can use more complicated constructs. So the thumbs up emoji, a lot of times you have the option to select different skin colors. That's used with combining marks. You have this base Simpsons-esque thumbs up sign in a interesting skin color. And then there's a series of emoji modifiers that are just combining marks that describe what skin color to put on that previous emoji. So this is Fitzpatrick, it's light white skin color. You can also get more complicated with just straight up grapheme clusters. For example, the cook emoji. We have a cook emoji here that's got a different skin color, which is, as you can see, it's based off of its 4 code points. It starts off with a woman, you modify the skin color, and then it uses something called a zero width joiner. With emojis, zero width joiners are used to say, hey, the 2 things that are on either side of me, they should be rendered together. Normally, if you did woman, emoji modifier, Fitzpatrick type 4, and then the cooking emoji, you'd have a woman of this skin color and then a cooking emoji. But when you add the zero width joiner in there, it just renders as a chef, a female presenting chef with a specific skin color. Pretty neat. Also, if you paste these into some text editors, like when I pasted this in VS Code, and then you highlight over the emoji, sometimes it'll break down that emoji as you highlight it into its component parts. It's like when I highlighted over this, I saw the woman emoji with the modified skin color and then the cooking emoji. And sometimes things just get absolutely wild. There is a single code point to represent a family, but Unicode wanted to be more inclusive. Not all families are a man, a woman, a daughter, and a son. You can have a man and a man, a woman and a woman. You can have a bunch of different combinations. They don't have anything for more than 2 kids, which, I mean, hey, that would get really interesting to try to render, but I feel like they did a fairly decent job. And for this, it's just you use the man, woman, girl, and boy emojis and join them all together with 0 width joiners. And you can get even more complicated than this. Like you can change the skin color of each one of these individually. So if you have a multiracial family, you can represent that accurately with emojis. You're just going to be doing the same thing that you do here. Take your base and then apply a combining mark and do that for each one of these components and then join them all together with 0 width joiners. I was going to try to do that, but support for those types of things is generally more on phones and less on desktop computers, so I wasn't able to render it properly, but that's something you can do. Also, country flags don't exist. The Unicode Consortium decided that they didn't want to deal with what is and isn't a country, which apparently can also be a very controversial thing. And it is. Just ask China about Taiwan. So they decided, nope, we're not gonna decide whose flags to encode. We're just gonna provide you 26 regional indicator symbols that you can combine however you see fit, and we'll let the vendors, the people rendering, decide what flags to include. So people like to use this in Discord to spell out messages in the reacts. Like I see in the questions here, somebody responded a few days ago with hack using these regional indicator symbols. But flags are just 2 indicator symbols next to each other. So for US, it's just the US. Pretty interesting. And if you copy this into, like I said, VS Code, and you hover over it, you're going to see it decomposed into those 2 regional indicator symbols. Also, some vendors like to kind of abuse emoji even more than it already is. This website that I was using is a pretty neat Unicode analyzer tool, and they had a suggestion for this ninja cat. It's like, what is this? I've never seen this before. So it's a cat face joined to a bust silhouette. It's like, what? This isn't a single emoji. Turns out it's a special emoji that Microsoft made for Windows. So this is on my Linux laptop. You can see it doesn't render. I switched over to Windows to take this screenshot, and it does render as a ninja cat. So even with emoji, it's going to wildly depend what your users see based on the platform they're on. So it's pretty interesting. And I think that's all. I forgot to add a resources slide, so I'll add that before the slides get shared in the workplace, because I found a bunch of really good links if you want to read up more about this. And I just want to finish off by saying, bring back Catos. I'm sad. I'm like the only person who's posted since June. Guys, what's going on? Where's your cats?
Awesome. Thank you, Newman, for presenting there. It was awesome.
Yeah, no problem. One quick question. Ray Dan says, what does this mean? Robber emoji may have existed and I'm not imagining things. Yeah, the robber emoji may have existed depending on what platform you're on. It's wild. But that's all I've got. Thanks, everybody. Really appreciate the chance to get to present, and hopefully I'll see you another time.